There. So nothing related to the class. Okay. Anything not related? No. I am used to answering lots of different types of questions, academic, life related, career related, that type of stuff. Office hours are better for those. And yes, I keep a box of Kleenex readily available at my office. There have been times. We won't go into that. Okay. So last time, I was talking about cryptography, or starting to talk about cryptography. I want to continue that here. Why did I lose my... So Idaho Fall, or Coeur d'Alene, you can see the slides, right? Yes, good, okay. So I was starting to talk about cryptography and talking about ways we do the more simple cryptography. So substitutions, where you just replace one letter with another, or transpositions where you rearrange things. So like the rail fence cipher, where it depends on the order in which you write things. When somebody is creating a crypto system, they worry about an adversary, an attacker, breaking that system. A crypto system is not good if the adversary can break it. So we do cryptanalysis to try and analyze our crypto systems to see how good they are. And bad guys also do cryptanalysis to analyze our crypto systems to see how good they are. I tell people, if you look at the National Security Agency, there's two basically main groups: ComSec and information assurance. Information assurance is responsible for protecting US government systems from attack. ComSec does the opposite. It owns our adversaries' computer systems, it owns the internet. The IA group builds crypto systems, the ComSec breaks them. At least roughly, they work together. So it's an interesting thing. And when I talk to people who build crypto systems, who do the math for cryptography, there's very complex styles of attacks. We won't go into most of those. That's beyond the scope of this class. Math 415 covers crypto at a much more detailed level. But some things I did want to talk about. So one thing we talk about is statistical analysis. If you look at the letters in a crypto system, the symbols, because it doesn't have to be letters, it could be numbers, it could be special characters. It's an arrangement of bits, just ones and zeros. Everything can be represented as that. Remember, bits are just bits. I actually have a web video about that for the class. They can represent anything we want. But when we're looking at natural language, when we're looking at English, we have the letters of the words. We have the letters of the alphabet. And they occur at different frequencies. So we talked about this before. The top 9 letters, E, T, A, O, N, I, R, H, S. In terms of frequencies, if you look at, I don't know, take a huge volume of books and analyze the character frequency. That's what you get. I wouldn't say take a dictionary, because what you really want is what people actually use in words in natural language. So E, 13% of the letters in an English text are the letter E. There's certain letter pairs, E-N, R-E, E-R, N-T, that are the most common, or triples, I-O-N, A-N-D, I-N-G, that are very common. So cryptanalysts can look at a message and say, oh wait, I'm seeing this repeat of these 3 symbols. These 3 symbols are very common. Maybe it's I-O-N, A-N-D, or I-N-G. If I have a simple Caesar style shift cipher where I'm just shifting all the letters, I can actually, and it's a long enough message, I can do a frequency analysis. I can see how many times does this symbol occur. So maybe N occurs roughly 13% of the time. And maybe another letter occurs, 10% of the time. And I can look at that and say, okay, I've got a mapping of these, and I've got the mapping of the English language ones, the natural ones, shift the new mapping over until it overlaps. And say, now I've got my key. I know how much I shifted. So that's an easy thing, especially with computer systems, for cryptanalysts to do. So we want to prevent them from doing that. We don't want them to be able to look at this and say, oh, it just shifted this much. We just did this type of substitution. That's easy. If they only did transposition, we know the same letters are there, so we don't have to worry about that. So let's make it harder. So Visionaire created a cipher that's like the Caesar cipher, but uses a phrase for the key. So if you think about the Caesar cipher, the key was 3. But it could be anything. It's how many letters you want to shift. We use a letter to represent that. So I said the key was D for letter 3. So here the key is VIG. The plain text is the boy has the ball. So the key, let me 2186, because V is 21, I is 8, and G is 6. And when we run out, we just repeat it. So VIG, 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 VIG is the key. And then we line up the T with the V. And we say, okay, T is what? 19. V is 21. That's 40, mod 26. So 19 to 21 is, mod 26 is 14. Remember, mod is just remainder. So 40 divided by 26 is 1 remainder 14. So that's an O, because we can look that up. H, which is a 7, I is an 8, mod 26 is a 15, that's P. E is the 4 plus the K, or 4 plus the G, which is an 8. So, or 6, I'm sorry. 4 plus 6 is 10. Mod 26 is also 10. So notice here we didn't have to worry about the remainder, so it's pretty straightforward, but OPK is our beginning, and it comes over. So now we have we have an H here, which is a P. We have an H here, which is a C. We have a B here, which is a W, and B here, it's also a W. Oops. The and the actually corresponded to exactly the same ciphertext. Well, that's annoying. I didn't want that. It was coincidental. If I had put in, if I said the boy has hat, well, no, I need something different. The girl has the ball. That would have changed the number of letters in the middle, and suddenly the 2 thes wouldn't have repeated. The fact that they can repeat, that they do align, is actually something cryptanalysts actually use and take advantage of. But the letter H isn't there all the times. Some other letters don't get the same mapping. A becomes an I here and becomes a, well, I here. Okay, wow, this was a bad example. It's supposed to help. So that was the idea. And you could do a longer phrase than just a 3-letter phrase, and that helps even more. So let's look at this one where the key is MEC. How would you decipher this? Right? You subtract the key instead of adding it, so you get back to the original. So here, I've got an I is an 8, M is the key, which is a 12, 8 minus 12 is -4. Wait, it's a negative. And I want to do the remainder. I hate that. But with remainders, it's easy. With mod, it's easy. Like 2 minus 5, in this case, that's a -3. That's the same as 2 minus 5 plus 26, mod 26. Because mod just gets rid of all the 26s in there as many times as possible. So we can add a 26. Any number, A plus 26 mod 26 is A. But here, at least, it gets us now a positive number. I should say if A is positive. Because mod never gives us negative. It's always it's not quite remainder, so it's always 0 or up. 0 to n-1 if we're mod n. And so to do the math easier, I just take 26 minus the number. So -3, 26 minus 3 is 23. 26 minus 4 for this first one. Because I said I minus or plus m, or I minus m. So 8 minus 12 was -4. So 26 minus 4 is 22. That's a W. So that should be a W. This next I, now we're minus E. So 8 minus 4 is 4, which is E. So WEP minus C. So 15 minus 2 gives us 13 is N, etc. And we can work our way through this. Anybody, I know some of you are writing. Does anybody get further than that already?
Well, no, I was just confused because you said the first one is W, but it says 23.
No, this is a hint. This is actually not for the first one. This is just a separate independent example, just to mess with your minds. Because I do that. I love the logic problems when they throw out a hint and it's meaningless for them solving the problem. Just messes with you. I'll come back to that example later because there's a good example. Anybody go further on this already? Somebody get like the first 6 letters, 8 letters? Anybody want to? Or should I move on? No answers. Okay. I'm going to move on. So we need more supplies fast, is what it decodes to when you do the full thing. Okay. And you can play with these and do these types of things. Okay, this was a more complex cipher. If my key is much longer, it's harder to break. Because now I have to first figure out what's the key length and then do a frequency analysis. So if the key length is 4, I do a frequency analysis on every 4th letter. And then I can say, okay, this is common every 4th, the next one every 4th, and find out, oh, these are the E's or these are the other thing. But you break it up as 4 separate ciphers, 4 separate shifts. Yes?
I'm a little confused. So
okay.
After you get, C minus P, does Q, like, when you figure out Q, you do M minus Q?
So actually it's P minus C, and then it'll be Q minus M again, I minus E, F minus C again, and then start over. So in this one, we take the ciphertext minus the key, or plain text plus the key. Yeah, and you repeat again and again. This is a simple, but again, it's a shift cipher. What if, instead of doing a shift, I rearranged this? So basically, I do the shift. I say, oh, the answer is 22. But that's not a W. I have another lookup chart, which makes it a different letter. That would be a style of a transposition, but do a transposition with a shift. So the Enigma machine basically did that. Which was what the Germans used in World War II. They actually had electronics. So you type in a letter, it went electronically on one side of a circle, and then came out another side. So it could shift everything on the keyboard, just rearrange them. And then they had 26 of those. And they rotated them to decide based on a key which one you wanted to do. So they kind of shifted these substitutions. So it took the Allies quite a while to break this until they captured one. Then they just had to figure out what the key was. Because they had the whole algorithm. Well, we know what it does, but how do we use the key? They found out the Germans were transmitting the key in plain text at the beginning of their messages. So, all right. How does this work? What does it do that makes it so strong? Well, there's 2 different things that we want: confusion and diffusion. Confusion is an encryption operation where the relationship between the key and the ciphertext is obscured. So a shift doesn't do confusion really as much. Okay. So if we can have each letter mapped to any other letters, we lose some of that operation. Diffusions where the encryption operation, where the influence of one plaintext bit or one plaintext letter is spread out over many of them. So I'm going to substitute for a word, a whole word. Or I am going to substitute, take 8 letters at a time and use that and substitute on those 8 letters, those whole 64 bits. So we're hiding statistical properties of the plaintext that way. Now, if I'm taking 8 characters, the E that's in there is combined with the T and the W and the H and all that, and it gets much more confusing. Okay, but it diffuses it, excuse me. I gotta be careful in those words. Okay, so how do we break this? If I have an encryption system and I have a solution, I could try what we call a brute force attack. I try all possible keys and see what happens. Most of the time, if I take one of these simple shift ciphers and I apply a key, I'm going to get garbage out until I get something that's suddenly, oh, wait, that's a word. That's a sentence. That makes sense. Now, more smarter than brute force than trying everything. Oh, by the way, let's assume there's 1,000 possible keys. On average, how many do you think you have to try before you get the right one? If I try this lots and lots of different times on different messages. Huh?
500.
Yeah, on average about half of them, 500. So we always look at that and say, okay, there's this many keys, divide by 2. On average, that's how many we have to try on a brute force attack. Cryptanalyst says, okay, can I do something smarter? Maybe a frequency analysis, so I can say, now these particular keys don't work, and I can reduce it further. Known plain text attack. Known plain text attacks, I know what the message is, or at least part of the message. Like if you're looking at a login to a computer system, there'll be part of that message that is password, : for entering your password or username, or welcome to the University of Idaho Computer Science System, whatever you see. It's a common thing. You know what it is. You don't have to, and so you can use that to help with your analysis to figure out what's the length of the key, what other things. Because if I see password, I see 2 S's. That may be not enough, but if something that's longer, I may see multiple letters. I'll say, oh, they're different letters. I know I have a different key length. I can start pairing things up. Usually in a known plain text attack, they get a larger message than just password that they know. They've received some other way. They know it's encrypted. And it was part of the message that didn't really matter, but it still got encrypted. Part of the document that didn't really matter, but still got encrypted. If it's a web page, well, there's certain standard header stuff at the top of the web page you see that's known. If it's a document, there's certain preambles in the documents that define document data types and other things that are well known. And they're always there in every document. Chosen plain text is even smarter. Can I force the encryption system to encrypt something I created? If I do that, then I have even more power of doing some analysis. And one of those types of analysis is called differential cryptanalysis. Okay, I just sent this whole message to you. You encrypted it for me. I'm going to change one letter. Change it. See what the difference was. If only one letter in the output changed, I know there's no diffusion. If many of them change, I get to see how much diffusion. If all of them change, I know there's quite a bit of diffusion. Could be I change one letter and I see the first 64 bits or the 64 bits surrounding that one letter changed, but the next didn't. Then I know what block size it is. Oh, it's working a 64-bit block. So I can start doing some analysis. One thing people have done with differential analysis on some attacks is look at it and say, okay, I'm going to change a bit of the key. I have a system. I want to see how strong the system is. I'm going to break a bit of the key and see, does it affect all the output characters or just 1 or 2 of them? How does the key map to the outputs? So look at the confusion. If only some of the key affected some of the output, that helps me in my attacks. I know what to analyze when and where. There's related key attacks. There's a birthday attack. We'll come to this one later, but there's what we call the birthday paradox. Birthday paradox states, so I have a birthday. I'm not going to say what it is, but let's assume it was January 1st. There's 50 of you in this room. Okay, not quite 50, but let's 40. Let's assume 40 people in this room. What are the odds one of you has the same birthday as the one I just announced, my birthday? People would say, well, if birthdays are evenly distributed, 40 out of 365, right? Roughly a ninth. If we look at the whole room, what's the odds two of you have the same birthday? It's greater than 50%. I think it's about 85% for 40 people. I actually have some slides about that one I'll post. Just because the way the math works, but it's like, okay, maybe you and I don't have the same birthday, but maybe you two, or you two, or you two. Well, none of you. Well, maybe you and you know, we get all these different pairings. There's so many different possible, you know, pairings. There's what, 40 times 39 possible pairings in this room of people. That's a big number. Okay, so the birthday paradox we can use to attack certain types of crypto systems. There's a downgrade attack where you force the crypto system to use a weaker version, an older version. There's pre-computing, I'll talk about that one later. There's implementation attacks where they just made it wrong. Social engineering attacks, hey, just get them to tell you the key, that's the easiest. Okay, so let's talk about some common encryption mechanisms. Common one, still used today, is the data encryption standard. It was designed for protection of unclassified data and published by the National Institute of Standard Technology, NIST, in a Federal Information Processing Standard, or FIPS publication, publication 46. Great federal government standards and guidance are in the FIPS series, the NIST, from NIST, and also the SP series, which stands for Special Publications. FIPS are standards, SPs are for guidance. They have SP 800 series is all on cybersecurity, great. And they do it for lots of different things, but cybersecurity is one of them. Anyway, the DES performs a series of permutations. So it's going to take your 8-character input, 64 bits, arrange it in a certain way, substitute things. Actually, some of you may not know this, so give me a second here. Oh, sure, it's not gonna let me do this. Shrink this just a little for a second. Okay. Oh boy, that's not really the best one. Let's see. Okay. I'm on the wrong table. Okay. Let's find a better one. That's a good one. Okay, ASCII stands for the American Standard Computer Information Interchange, or American Standard Code Information Exchange. I can't remember the exact one. But this is how we encode basic keyboard characters. So if we look at, these are decimal. This is hex version. Hex is base 16. Right, so 20 is 2 times 16, 32 plus 0, so decimal 32. That's a space. If I go down here, capital A is a 65 decimal, capital B is 66 decimal, capital C is 67 decimal, lowercase 97 decimal. The difference between these two, by the way, look, this is 41 hex, if you can see that. Lowercase is 61 hex. It's just, when we write these out as bits, it's just changing 2 bits or adding 20 hex to go from capital to lowercase. They did that deliberately. So this is from 0 to 127. That is 7 bits of information. And you can represent these using zeros and ones, right? So 7 zeros get you a 0. 0, 0, 0, 0, 0, 1 is a 1. 0, 0, 0, 0, 1, 0 is a 2. 0, 0, 0, 0, 1, 1 is a 3, etc. So binary representation. And they just go through. So, you know, the lowercase ones, all the first 31 are control characters, like backspace, ring the bell, line feed. Ring the bell is for the old line printers and your old typewriters. But sometimes you'll hear a ding on the computer too. End of medium, substitute, escape, file separators, lots of different things in there. There's a line feed. Let's see, form feed is character 12, line feed is 10, carriage return is 13. So go to the next line, back to the beginning, or just straight down. All these characters are there. The reason I'm bringing this up is because I forgot. Why am I? There's 7 bits to represent all these characters. In the old version of ASCII, we could do that, and we could use the 8th bit as an error check, what we call a parity bit. And if we had even parity, that bit would tell us, would be 1 if there was an odd number of 1s in the rest of the character, so we'd end up with an even number of 1s. So you always, even parity, always an even number of 1s, and you can check, oh, we had an error because you have an odd number of 1s, you're supposed to have even. And it could, you know, detect a single bit flip in a transmission error. DES assumed you were using ASCII. DES assumes, I have to shrink this so I can get back to my other slide, that the key is also an ASCII that has the parity bits. So DES actually throws out that parity bit. It takes 8 input characters, but only pays attention to 7 bits from each character. 7 times 8 is 56. So it uses a 56-bit key. And it uses a 6, but it takes the whole 64-bit message and encrypts that, so it preserves the parity when it decrypts it. So it takes 8 characters, each 8 bits long, 64 bits, switches those bits around, does substitutions, recombines them, does all that. 64 bits in, 64 bits out. Let's see if I got this. The key, like it says, 56 bits, not considered long by today's standards. Exhaustive key search. So 2 to the 56 possible keys, 2 to the 55 on average you have to search. Actually, you can do a little better than that with DS. That's still a big number, but modern computing system, we're talking minutes. Okay. Double DES or double DS, each 64-bit block is encrypted twice with the algorithm, each using a different key. And there's a triple DES, which I'll talk about. Triple DES uses 2 keys, you encrypt, you decrypt, you re-encrypt. So you encrypt with key 1, decrypt with key 2, re-encrypt with key 1. And that's actually considered much stronger. So it's under 28-bit key length and much stronger, and it's what's recommended current days if you're gonna use DES. Years ago, banking went to using triple DES before newer standards came out. Oops. Hey, I put slides in here and they're not here. Well, that's a bummer. Okay, I wanted to show you 2 things, so I'm gonna have to search again, sorry. I bet I didn't save them. Okay. So the DES algorithm, what it does is, if you can see this, hopefully, and I'll put these in the slides, but it takes your first initial 64 bits and shuffles them around. That's what we call an initial permutation. Then it takes those 64 bits and splits it into 2 halves. We have the left half and the right half. The right half is copied and becomes the left half on the next phase. When I say next phase or next stage, they do this 16 times in the algorithm to make it more complex. What I find is really cool here is this, the right half is also used. They take those 32 bits and expand them to 48, combine them with 48 bits from the key. So the key goes through also some shifting, and they take the 56 bits, do some changes to it, take 48 of those 56, put it for stage 1, do some more changes to it, take another 48, give it for stage 2, etc. All right, it takes these, combines them, the key with these expanded bits, then puts it to what we call a substitution box, which takes every 5 bits of this expanded, reduces it to 4, or no, 6, reduces it to 4, and creates a new 32-bit output. All this 32-bit output, oh, and then they shuffle it again, permute it. So all this 32-bit output is some combination of these 32 bits, this right-hand side of the plain text you want to encrypt, and the key. And it does, substitutions and permutations, does all these changes. Then it takes that and combines it with the left side using an exclusive OR operation, which I'll talk about later. So we combine the left side and the right side. This basically substitutes the left side with this automatically generated substitution. And that creates a new right side. So it takes the left side, combines it with this new right side. The new left side is the old right side, no changes. So, but now the next phase, we do this again, and that old right side, which is now the new left side, now gets combined. And so every other phase, half of the box is encrypted. The bits in this right side being permuted and substituted influence the bits of this output right side. And in a way that's shuffled, so we get diffusion. These 32 bits are diffused across these bits, these 32 bits. These 32 bits, they line up 1 to 1, but then they get diffused across the other ones on the next phase. And so we start doing a lot of diffusion. And then they do this 16 times. It's called the Feistel style algorithm. The beauty of this is you can go through the same exact algorithm, just reversing the key schedule, and it decrypts. What? So the key schedule is you start with the main key, you do some shuffling, you get sub key 1, 48 bits of that, and you use it here. Then sub key 2, 3, 4, up through 16. You reverse the order of those keys these sub key generation. So you start with sub key 16 and it starts decrypting things. Don't worry about it. The beauty of it, you can use one piece of hardware to do both encryption and decryption, or one algorithm to do decryption, decryption, by just changing the keys, the order in which the key is processed. So that was kind of a cool thing about it. All right. There is a problem with DES. There's something called the meet in the middle attack. Soon the attacker knows a set of plain text messages, right? And ciphertext messages. And we have 2 different encryption keys. Okay. Or actually here, I should step back one. There's a lookup table attack. If I use a single DES algorithm with a single key, what I can do is I can say, hey, here's a whole bunch of common words. Here now is a set of encryption keys, all possible keys. Let's take these common words and encrypt them completely. Now I got a lookup table. When I look at your ciphertext and go through your ciphertext, and there's password : I know that's going to be in here. Here's password. Password's 8 characters, right? I know that's going to be the first of a block. That one exactly matches this. I know what key was used to create that. That was my match. I win. When they first were encrypting people's passwords, they actually did this. They took the password, they encrypted with DES, they stored it in a table. But then somebody quickly figured out, hey, I can pre-compute these tables on some common passwords, try a whole bunch of different keys. I found it. So what they did then is they changed the DES algorithm basically. Oh, I don't have it now. That first permutation, I said they met with passwords, they use a seed, and we'll talk about this later. Well, there's a 12-bit seed. They changed that first permutation based on that 12-bit seed. So there's 4,096 possible permutations they used just to make these pre-computing 4,096 times harder. Anyway, with double DES, they thought, hey, we solved the problem. We made it a lot harder because now you got to try to pre-compute using the whole 112-bit key. And what they figured out is, so we can encrypt with key 1, then key 2. The problem is, I could pre-compute everything encrypted with key 1, And now all I have to do is, oh, I've got your ciphertext, I'll decrypt it with key 2, and then I'll look up in my table and see if it's already there, the key 1 part. And so they basically found there was an attack, smart attack cryptanalysts they use to make double DES not very effective. It's a little slower because you got to do this extra decryption. But I just wanted to mention it's out there. We're not going to talk about this again. Just wanted to know it's out there. So to break normal DES with known plain text, we try 2 to the 56 possible keys. Double DES, they thought it was 2 to the 212 bits because you had 2 56-bit keys. Meet in the middle. You prepare it with 2 to the 56 times, and then you try it. So I prepare it once with that known plain text, and then I try all possible keys to see if it's there. It's 2 to the 57 possible strength, not 2 to the 112. And I just say this because you can see that's a tremendous reduction. It's only twice as hard as regular DES. Double DES is twice as hard. It's not exponentially harder. And this is something people run into when they try to build their own crypto. They miss the smart, intelligent attacks the attackers do. All right. So triple DES came out. IBM also helped invent DES in the 1970s. Triple DES was developed by a team led by Walter Tuchman. It prevents the meet in the middle attack. It has a 168-bit key. So I was wrong, it actually uses all 3 keys. So you encrypt with key 1, run it through the decipherment algorithm with key 2, and then re-encrypt with key 3. Now this doesn't actually decipher because you have the wrong key. So it's like garbage out, but it's another way of enciphering. But because you switch the order in which it's run through the algorithm, it makes it harder. And it's compatible with using double DES. Because we can do it this way. And it's also compatible with single DES. I can do encrypt with key 1, decrypt with key 1, encrypt with key 1. This would give me back the same one. So a piece of hardware that does triple DES automatically can also be retroactively fed with single DES. And we can do it with just 2 keys, make it a little weaker. Okay, so just triple DES, it's just encrypt key 1, decrypt key 2, encrypt key 3. Just remember that. Okay. DES actually has some weak keys. There's 4 keys that don't do very good encryption. And these are the 4. In just the way the master 56-bit key creates these sub keys. And because the same sub key is used in more than one round, so it becomes not very effective. It actually, I think the way it works is it deciphers the previous round if you have the keys in consecutive rounds. So it makes the whole thing a little weaker. So there's another thing cryptanalysts have to look at is, and cryptography designers, are there weak keys? Are there things that where it makes the system not as strong? All right. So if we look at this, this is the important takeaway. DES, you encrypt with 1 key, key length is 56 bits, strength is 56. Double DES, 2 keys, strength's only twice as hard. 2 key triple DES, strength is like an 80-bit key equivalent. Because there are some kind of partial meet in the middle attacks there. 3 key triple DES is 112-bit strength. Not a full 160 something bits, but still strength 2 to the 112th possible tries, operations they have to do. That's a lot. That's a big number. 2 to the 32 is 4 billion. Go up from there. I don't know what 2 to the 100 is. I know it's just a big number. Okay, AES is what we call the Advanced Encryption Standard. It was adopted in 2001. So in the early 1990s or mid 1990s, NIST said, we need to do something better. DES is not strong enough. Computers are advancing faster than we hoped. Put out a worldwide call, create a new standard that can be fast, implemented on hardware on a simple processor. And so a whole bunch of people put them out. There was actually a team, I think, from the Netherlands that did Rinjdal. I can't remember if it was Netherlands exactly, could have been Norway. Anyway, theirs was picked as this one. And they picked like 6, went through much further rigorous worldwide analysis of these, and then came up with this one. So it also uses substitution, transposition, and shifting things around, and exclusive OR and addition operations. No multiplication, because multiplication is slow. But substitution, permutation, shift, exclusive OR, all are fast. It uses repeated cycles, they're called rounds. It has 3 different key sizes. You can use a 128-bit key, 192-bit key, or a 256-bit key. And then it uses 10, 12, or 14 cycles for the keys. And each cycle consists of 4 steps. So cycle around. The steps perform both confusion and diffusion on the input data. And the bits from the key are combined with intermediate results frequently, so the key bits are also well diffused. And it's all implemented, so it could be done in hardware. So that's cool. It's out there. The algorithm is more complicated to explain, but it takes the message, splits it over multiple rows, does different shifts and transpositions on the bits in the rows, and then combines those and all. It's been out for 20 years now. Hopefully everybody's using it by now. It's probably old. So I talked about exclusive OR. I'm going to come back to this because we use exclusive OR a lot. It's a very common operation in cryptography. What do I mean by exclusive OR? When you have bits, 1s and 0s, it's exclusively either a 1 or a 0. If that is true, you get a 1. So 1 exclusive OR with another 1 is a 0. 1 exclusive OR with a 0 is a 1. 0 with a 1 is a 1. 2 zeros is a 0. So I can take this first set of bits, exclusive OR with another set of bits, and we just line the bits up. So 1 exclusive OR 1 gets me a 0. The next ones get me the 0. The 0 now exclusive OR with the third one here. The 0 with the 1 gives me a 1, etc. The beauty of this, if I go backwards, if I take this bottom one, exclusive OR with this same value again, I get the result back. So 0 exclusive OR with 1 gives me a 1. 0, 1 gives me 1. This one now with this 1 gives me a 0. So you exclusive OR with the same thing, you get the same answer back. That's nice. It's actually, could we use this for cryptography? Yes? Why do you say yes?
It's easy to encrypt and decrypt.
It's easy to encrypt and decrypt because I said it's a common operation in cryptography on the slide. But yeah, it's easy to encrypt and decrypt. Now, what's my key? Depends. Depends on the algorithm. The key could be something that generates the streams of 1s and 0s that you use to exclusive OR with. It could be the key is that stream of 1 and 0s. There is something called a one-time pad. The idea is that it's a non-repeating key. So think of the Vision A cipher, but you go forever on your input. Non-repeating key, right? So I could use that. I could have a sequence of 1s and 0s that's non-repeating. Maybe I represent pi with them, right? That's non-repeating. And you know how it starts, and I know how it starts, so we can line up our 1s and 0s. I can send you everything exclusive OR. It looks random. And you can decipher it easily. The hard part is getting us to agree on that starting point and what that one-time pad is without anybody else knowing. Quantum cryptography, quantum key distribution actually does that, but we weren't going to get there. Okay. There are some challenges when we come to symmetric key cryptography. First, which I will not talk about on this slide, I will talk about later, is getting us to share the keys. So you know the key, I know the key, but they don't. Second is how we prevent attacks by the cryptographer or the cryptanalysts. So I want to prevent replay attacks and known plain text attacks. What's a replay attack? Oh, I see a message going across the internet that says transfer $1,000 from your bank account to my bank account. I hope you have 1,000. I hope you have a couple thousand because I'm going to do this more than once. I'm going to take that same encrypted message. I know I got it forced to happen. I knew he was transferring the money. I got to watch it happen. And then I replay that exact encrypted message again. Or maybe we have a message that comes across that where I'm transferring $1,000 to you. You're welcome. And then I take that same message. I know how it's arranged, and I switch the source, the from and to bank account numbers. So I get my $1,000 back. If I can line things up just right, I can do that. Virgil Gligor, a cryptographer at University of Virginia, gave a wonderful talk about this in the 90s, how people were implementing crypto wrong. They were lining up these blocks. So, hey, I know what's in this block. I know what's in this block. So I'm going to switch them. So there's a mode of encryption called the electronic code book where we take each plain text in DES, we take our 64 bits and encrypt it with the key. And the next 64 bits, we do the same thing. And the next 64 bits, we do the same thing. So if we can line these up just right, we can start replaying things. So that gets me a problem. Also, stream of data. What if my thing isn't 8 characters long? Gmail, my user ID is 5 characters. Then I hit return, that's 6. What does it do? Like I said, it pads. Well, that pad is things that I can do things with. Not as much confusion, not as much diffusion. How do we do that? So one common, very common way of doing this is something called cipher block chaining mode. The idea of cipher block chaining mode is the following. At the top here, I have my plain text. Block 1, block 2, block 3. First 8 characters, next 8 characters, et cetera, up to block n, okay? I take an initialization vector, so something random that is agreed upon between you and me. So we not only know the same key, we know the same initialization vector. That's important. It exclusive ORs, we just talked about what that is, with my plain text, and encrypts that with the key. That gives me a ciphertext. That ciphertext is then fed back, chained back in to the next block, an exclusive OR with the next plain text. And we encrypt that with the key to get the next ciphertext, etc. To decipher, we take the ciphertext, decrypt it with the key. Well, that's this output here. So I have to then exclusive OR it with the initialization vector. We can, because exclusive OR undoes what we did. And we get the back. And we do the same thing with the ciphertext. So if it happened to be that this block and this block were the same, exactly identical, I can't replay it. I can't repeat it because this output ciphertext depends on the previous input ciphertext. These two ciphertexts, even with the exact same plain text input, will be different because I've diffused all the previous message over this. And the important thing too is I take this ciphertext, I feed it in here, combine it. This ciphertext now was derived from both blocks. The third one I do will be derived from all 3 blocks. So every ciphertext is dependent upon all the previous bits of that message. And we're really, as we get further and further, we do more and more diffusion. So that's a cool thing. What happens if an attacker comes in and replaces this ciphertext? So let's assume we're in the middle of the message, they replace this one. I'm gonna make this easier. It comes through, we decrypt it, we exclusive OR it with the previous ciphertext, and we say, oh, that's garbage. They broke it. They replaced it though. They did a substitution. What happens to this next one? They gave me a ciphertext. I'm using that to decipher this good block and exclusive ORing. It breaks that one too. But then this ciphertext, the good one, is used to decipher the next one. I'm good again. So one attack on one block will break 2 blocks in this mode. Electronic code book mode, it'll break 1 block. Here we'll break 2, but not all of them. So even though it's diffused across, the moment we can resync and get the right ciphertext back in, the next blocks forward will be good. There's another mode called cipher feedback mode. And all of these are modes that are built in now into the standards, both for AES and DES. Here, I like this one I'll explain this in a reason. I take the initialization vector and I encrypt it. And I exclusive OR that with the plain text to get me my ciphertext. I take that ciphertext and encrypt it with the key again, and exclusive OR that with the plain text. I'm actually never really directly running your plain text through my encipherment algorithm. I'm running the initialization vector and then your old ciphertext through my encryption algorithm. What this allows me to do is if this plain text was only GMAF colon or GMAF return, so 6 characters, I can exclusive OR those first 6 characters and send them on. And I can wait on the next 2 before I move on and send those. So I can take this block cipher and convert it to a stream cipher by doing this. So it can do one character at a time, 1 bit at a time, whatever it needs, and not have to do the full block. And yet I still get all that diffusion by mapping things through here, because I took the plain text and combined it with the key and exclusive OR'd it, and I map things around. So I still get things encrypted. This exclusive OR is a good encryption because the only way to undo it is to know what this stuff is, know what the key is, know what the initialization vector is. The only way to do this one is to know what the key is in the previous ciphertext block. Okay, let's assume you got that, but you have to know the key. Okay, so it's a good one, and it's faster because it allows you to do stream. You don't have to wait for the full block. There's output feedback mode, where now you take the initialization vector, encrypt it, and then encrypt it again, and encrypt it again, and encrypt it again, never feeding anything back in, and then exclusive OR those with the plain text. Again, this generates a stream of 1s and 0s. Because we keep re-encrypting the output here, it's generating a new set of 1s and 0s. It's what we call a pseudo-random number generator, because it's a random set of 64 bits every time. So it looks random. It's not really random because if I started with the same initialization vector, the same key, I'd get the same stream of these out. But like I said, again, I can take plain text and just do this. I can also pre-compute a lot of this. So if I'm suddenly get a burst of plain text traffic, say a video or something, I can just do exclusive OR really fast because exclusive OR is a fast operation. You know, you're gonna have a hardware gate just like, oh, 1 and 1 is 0, 0 and 1 is 1, we're done, move on. There's exclusive OR gates that just do this really fast. You don't have to go through these 16 algorithms of permutation, substitutions, all that. And so if we can pre-compute some of this and handle bursty traffic, this works really well. So these modes are really, really useful to understand. As a computer scientist or as a cybersecurity person, a person using crypto, writing code that uses and develops crypto, you may be forced to come up with this type of feedback mode. I have a crypto engine, I want to make it stronger. I need now to implement. I'm not going to implement DES or AES, that's already done. I'm going to implement a mode on top of it. Now, most of these modes are built into modern chips and software, so you don't have to, but it's something to think about. This is the level I want you to understand crypto. Not how DES works or AES works, because that's really hard. The modes is easier, at least in my mind. Of course, I've known about these for longer than you've been alive, but at least most of you. There's another one called the Galois counter mode, which is a similar type of thing. It takes a count initialization vector into a counter, increments of the counter, encrypts the counter, uses that counter to exclude the encrypted version of the counter, exclusive over the plain text to get the ciphertext, then uses that ciphertext combined with some authentication data, so additional password or something, combines those together to get a final, what they call authentication tag to say, hey, I'm the one who actually sent this encrypted message. I'm just showing you that it's out there, these exist. You don't have to understand this one. It just exists, and it's a modern one. You Google encryption modes, you Google, cipher feedback mode, you'll get these 4 or 5. ECB, electronic code book, is just 1-to-1. Cipher block chaining, cipher feedback mode, output feedback mode, and Galois counter mode. I think there's another one out there too, but these are the most common ones I see when I look things up. So electronic code book, it's simple, it's fast. It supports parallel encryption and decryption. I can take your whole block of text, your whole file, break it up into 64 chunks, and run them simultaneously through a bunch of parallel computers using the same key. That's fast. A duplicate data in the plain text is repeated in the ciphertext if it aligns up in those blocks. I can change plain text by just changing the ciphertext. If I get lucky, I changed it the correct way, and you just lost your $1,000. It cannot resist replay attacks. It should not be used. Cipher block chaining supports parallel decryption, because if I have your whole cipher text for your whole document, I use those to feed back in to help decrypt the next one, right? So I can use those, not parallel encryption, but decryption. I can decrypt any ciphertext packet. Duplicate data in the plain text is not repeated, but does not support parallel encryption. And a corrupted block affects a subsequent block. Cipher feedback mode. We don't need padding. That's a good thing. Again, we support parallel decryption. We can decipher any ciphertext packet. We can prepare keys for encryption and decryption ahead of time. But like I said, doesn't support parallel encryption, just decryption. Can't resist replays. In this case, corrupted block will affect subsequent block. I don't know, what am I, can't resist replays? I'd have to look at that one. I think you can. I got this from a book. Output feedback mode, no padding needed. Can prepare the keys ahead of time. Corrupted blocks do not affect other blocks because the keys are independent of the previous ciphertext, but does not support parallel encryption or decryption the way it's set up. Again, that doesn't sound right. All right. Output feedback mode. Yeah, it should support parallel encryption and decryption. That's a typo. As long as we prepare the keys ahead of time, we're good. Okay. Encounter mode. We could change some ciphertext from plain text undetected in just the way it works. Okay, yes.
Can you go back to that again?
Which one? This one?
Which one has the typo next?
So output feedback mode does support parallel encryption, and I will fix these and post them. Yeah, so. Because that's not in the book. A lot of this is not in the book. There are some challenges with symmetric keys. Okay. So one was just using it to avoid plain text and known plain text attacks. How do I get us to agree on the same key? If a secret key is known by the attackers, I lose. They can later read, modify, forge all messages encrypted and authenticated using that key. Key management. So the generation, transmission of storage keys and storage of keys is important. Key management is a key part. Okay, that's bad. Key management is an important part of cybersecurity, of cryptography. It's, again, the more important part. I tell, think of at my home, I've got a deadbolt on the door, but if the key is under the mat, that's poor key management. Somebody can lift the mat and grab the key. If I don't lock the door, that's poor key management. Okay. There are also ways you have to be careful that they bypass it. I may have told this story already. I rented out my house when I was on sabbatical 20 years ago. When I came back, I had rented out for a year. I was gone for the year. I came back. The tenants were gone. They had, while they were there, somebody changed the lock. So I had my key. I couldn't get into my own house. But fortunately, they'd steam cleaned the carpets. So I had my front door all locked. Next to my front door was a big plate glass window open, the screen just there, so it can air out the house. I popped out the screen, went in the house, bypassed the security mechanism. Okay, just shows you misconfigured windows is a security vulnerability. Okay, that's my 20-year-old joke. Okay, and it's still been around. But it happened, it's true. So key management is a really important thing. If somebody gets your keys, you lose. All keys in a secret key crypto system must remain secret. Secret key or symmetric key cryptography often has problems with secure key management, especially in open systems with large number of users. The other problem is, what if I wanted to communicate with everybody in this class, but just this class securely? We could all share the same key. I have to get it to you all secretly. But any one of you could then use that to send a message to everybody else pretending to be me. There's no authentication involved. And what if I wanted to communicate with each of you independently and individually? I'd need 50 different keys, and each of you would need 50 different keys. And that's just for this class. Key management gets to be a real issue. So that's something we want to deal with. Okay, but symmetric key or secret key encryption, which is all we've been talking about so far, we involve one key for using both. They're common algorithms, DES, double DES, triple DES, AES. But replay attacks, known plain text attacks are a possibility, and key management's a problem. How do we fix this? Do we fix this?
Asymmetric keys.
Asymmetric keys. Non-symmetric keys. Whitfield Diffie and Martin Hellman introduced the concept of public key cryptography in 1976. Actually, I think people were talking about it before that. I do remember a science fiction story that I read back prior to that, a short story where they had this new public key algorithm, but they needed to initialize it by sending the first version of the key to Mars. And so there was a guy on a spaceship bringing the algorithm in this first key to Mars so they could set this whole thing up and do it. And his ship was attacked and people stole. Anyway. Okay. So we use what we call public key cryptography to solve this problem. And public key cryptography can use for this key management, this key distribution, can be used for confidentiality. I want to send you a secret message. Can also be used for authenticity. You know this message came from me. Can be used for data integrity, error detection. Can be used for digital signatures, which is kind of like the authenticity issue, showing you I really created this document. Asymmetric cryptography basically means we're going to have a pair of keys, two keys. So instead of us both having the same key, symmetric, asymmetric, I have one key, you have another. The whole idea here is that I can encrypt with key E, you decrypt with key D to get back to plain text. These are completely different but related keys. Have to be related, because if they're not related, then the system's broken. Okay. And the two keys have the property that deriving the private key from the public key is computationally infeasible. You have my public key, this decryption one, that you can use to prove the message came from me. And nobody should be able to use that to figure out my private key with a really robust computing system. So the private key is the secret part, typically used to digitally sign a message and I'll show you how this is done to prove it's from me, or to decrypt. If you want to send me something secret, you encrypt it with your public key, my public key, and I'm the only person in the world who can read it, theoretically. Public key, the other way around. Okay. Each user in the network then has their pair of keys associated with them. The public key, like I mentioned, and the private key. All communication involve only public keys. No private key is ever transmitted, ever shared. My public key can be out there in a directory, published for the world to see. Here's my public key, doesn't matter. And the pair of keys is generated using a key generation algorithm because it's complex to have these related keys. The mathematics of public key cryptography involves complicated mathematical manipulations of large numeric numbers. What do I mean large numeric numbers? 128-bit, 256, 512, 1024-bit numbers from 0 to 2 to the 1024. Okay, these are big, big, big numbers. Okay, your calculator can't handle that. Okay, most normal computers cannot handle them. You have to have special software designed for big num calculations, what we call it. All right. And public key crypto systems are usually, we can system as a network of users. Because if there's only two of us talking, we can do a symmetric key. But if I want to be involved in network and communication, I need this. Okay, and again, these slides are repetitive. The public key, the private key, etc. Okay, for confidentiality, you encrypt with my public key, I decrypt with my private. For authenticity, I encrypt with my private. I send it out there. Everybody can decrypt it. If they decrypt a valid message, they know it came from me. Because I'm the only person in the world who knows that private key, theoretically. But it can encrypt and decrypt both the directions. And I just realized I'm missing the E's in these for encrypt. Okay, yes,
How can you encrypt with one key and decrypt with a different key?
we'll show it later. Probably next lecture. There's some complex math that works with it. The RSA algorithm, Ravi-Shamir and Edelman's algorithm, uses modular arithmetic and exponentiation to do it. There's versions using elliptic curve. And I can't explain how that works, but that's actually the better way nowadays. All right, so secret key, just a comparison here real quick. Secret key has one key, public key has two. Key size, DS5 or 212 bits, 128 to 256 AES. Public key, unlimited. Shouldn't be less than 256 bits, typically 1,000 to 2,000 is currently used. Like you definitely need a lot more bits to be as strong as the symmetric key, just the way it works. I think a 512-bit RSA is equivalent, or no, a 256-bit RSA is like equivalent to a 56-bit DES in string. Key must be kept secret. One key must be kept secret, but the other one exposed. This is a cryptographic workhorse, secrecy, integrity of data from single characters to blocks of messages and files. It's fast. DES is much faster than RSA. A symmetric key is always much faster than a public key. And so we'll talk about ways of taking care of that so we get the speed of the symmetric key and the security of public key. But I think I'm going to stop there because now I got to go into, let's see, I can do this. There's some misconception about public key. It's more secure than symmetric key. Actually, it all depends on the length of the key and the computational work involved in breaking it. I just said the power of symmetric key. The power of symmetric key is key distribution. I can give you the public, or as asymmetric key, I can give you a public key cryptography. That's the power of key distribution. Public key is easy to get put out there. It's a general purpose technique that made symmetric key outdated. No, it's slow. Public key is slow, 100 times to 1,000 times slower than symmetric key. Key distribution is not important to public key compared to key distribution needed. I just mentioned it's easy to put out the public key. How do you know I'm the one who put out my public key? Maybe he put out my public key claiming to be me. How do you know what's really me? We still got to fix that problem, but we'll get to that. Okay, so we're going to talk about how we do this first to exchange secrets and then to protect confidentiality. But I'm going to do that next time because I'm running out of time. A couple of things I want to mention first before we do this. So let's see, stop my share. Stop recording.